So I'm going to go ahead and give a talk on blockchain technology in the smart city, a bibliometric review. Actually, that's going to be about the middle 10 slides out of 50. I'm not going to be reading the slides because it's going to be far longer than this talk could possibly be, but they're there as a reference, and I will, of course, highlight everything on each of those slides. So first off, I want to thank Donna and Chris and also Lisa for setting me up to do this. This is a wonderful event. It's really cool. I did not know about Boise State's event here, and I'm very pleased to be part of that. Also, I will mention I am a member of IEEE as well, and I'm in the High Plains section out here in Colorado. So it's a really excellent organization. I'm going to go ahead and get started with the slides, and I'll talk about a few things as we go through. So one of the things Donna mentioned was the Whittier Glacier, which is what you're seeing here up at the top of the slides. It's actually in Whittier, Alaska, and it's south and a little bit, I guess, a little bit east of Anchorage. You have to kind of drive down towards Seward. To get there, it's a one-way only. It switches between direction tunnel that's about 10, 12 miles long. And so you go one direction, and then about half an hour later, it switches and you can get out or go in there. And Whittier is one of the foggiest bays in the country. And it was actually set up during World War II because they figured the Japanese couldn't find the inlet to it because it was always fogged in. So it's a very interesting town, and the entire town lives in one Stalinist-like building. And I'm not making that up. There's about 200 or 300 people that are there. So that is a super cool place. That's what Donna was talking about. That is not, however, the talk that I'm going to give. The outline of the talk is I'm going to talk about blockchain and distributed ledgers. And that's actually going to be a big part of the talk, because for us to understand the relatively small contribution of our paper, which is still a nice paper, but we have to look at the large contribution of distributed ledgers and see how blockchain fits into that. And then I'll talk a little bit about verticals of interest, but I'll probably gloss through those in, no pun intended, interest of time. And then I'll talk about illicit trade and some other perspectives on that. What we have below here is basically a skeleton of the abstract of the paper. The talk itself is going to cover each of those topics we're seeing right there. So trying to close down this thing up here. There we go. So the highest level overview that we've got here is that that every blockchain should be used for a positive purpose. And if it's not, it's probably being used for one of these negative purposes that we see right here: non-transparency or unnecessary anonymity. And we see that a lot with blockchains, and we'll see why, because actually to have a blockchain, you also need to have a set of public and private keys, or something analogous to that that's distributed. And instead of going through a CA or certification authority, that will come from a blockchain wallet. So there still has to be the ability to distribute these private keys that allow us to basically use these things together. And then there's also intentional inducement of volatility. And this happens all the time. People love to have Bitcoin, for example, because it's very volatile. If you're in the financial industry and everything just goes up slowly, it's harder to make money out of that. But if it's going up slowly, organically, but it's waffling back and forth, there's ways to make money both when it's going down and when it's going up. And so a lot of the excitement around blockchain-like technologies is actually around the volatility, because it's an opportunity to make more money than if something's really going up in a steady form. And of course, going up in a steady form benefits the people who are part of that. Then there is non-sustainability. And we know that with the blockchain algorithm, there is a need to basically generate gigawatts of energy for them to be able to get the next logical block in the blockchain. It usually is done with, you have to add an extra zero on when you hash it. So you go through billions, actually billions of hashes until you get the next one out there. Again, not a good method. If you end up with something that allows people to anonymize the illicit activity, you allow them to induce volatility into a process so that the people who own the process can make the money, which means the other people lose in the money. And then non-sustainability, where you're actually losing a lot of energy through this. So all of those are reasons not to be doing blockchain. If you see that those are being used, that is definitely sus. That is an imposter right there. All right, so let's take a look at this. Blockchain is one particular embodiment in a continuum of security technologies that we call distributed ledgers. And a ledger is simply a type of database. They've been around for a long time. I show the GS1 here because they've used a ledger-like technology for decades. And so a ledger is a type of database, whether it's an offline book used for record keeping or an online database of transactions. in which people are participating. And it can be kept personally like a budget, but often it needs to be shared for only the right set of people, those who are logically involved, to be part of. And as a supply chain example, which I show over here, this has been around, traceability and blockchain in GS1 for many years. The shipment details from a shipper to a buyer might be relevant. What we'd actually do is have them signed by the sender and then signed again by the recipient, and you have this sequential signature that's out there. It's simply a list of digital signatures, and the blockchain works similar to that. So the latter type of ledgers I've talked about is shared across nodes in a network. That's why it's called a distributed ledger. And it's essentially an asset database, right? So and assets can be anything. I mean, but we're talking about digital assets largely that can be shared across a network of multiple sites, of geographies or institutions. And so anyone within the network can have their own identical copy of the ledger. So once the private keys have been distributed and we have the public keys there that validate that the person signed that with their private key, the parties that are there can all validate every other party in there through the posted public keys that go along with this. So the number of parties that are purposely involved in sharing the ledger depends on what the workflow is, and that's why it's so adaptable. And so in the case of a blockchain, which again, I remind you, is just a distributed ledger, the distribution parties are selected as a balance between requiring a certain level of consensus and then slowing down the system to validate that consensus. And again, you don't need to be running the blockchain algorithm with a bunch of zeros at the front to use a distributed ledger. So we put this in context of doing multiple distributed ledgers, and I'm not sure why I'm not able to get rid of this thing on the top of my screen, so I can't see the title of the screen. But anyway, trust. Due to the nature of being shared and requiring identical copies, DLTs include security protections that we use across the board. And so we have an example of overloading. And those of you who do C++, my little pun over here, recognize overloading, where we have multiple methods that do the same task. DLT can be viewed as an overloaded method, where we have on one continuum a distributed ledger of one-time pads where they only go out to people who need to know that. So a one-time pad goes way back in history. Originally, they were little tiny notebooks that people had that allowed you to XOR data that was there. And unless you knew what that XOR was, every possible translation of the data was equally likely. And then on the other hand, we go to a fully distributed ledger in which every potential party to a transaction or set of workflows or other set of digitally changing content is required to keep a full account of every record. That's a massively parallel system. And so we see there's a continuum between all of those. And I'll talk about each of those as we go through here. But blockchain sits in the middle of this. It's not a fully distributed ledger like we've talked about, and it's not a one-time pad where if you lose the pad, you cannot translate the content on the other side. And an individual block that's within the chain contains several electronic elements, and this will be the block number, the timestamp, of course, so that we know when this was done. The timestamp is also signed, that's the definition of it. And then the data transaction stored within the block, the previous block's hash, and then the hash of the current block. And with all of those, you can establish who authorized this, you can validate that they signed this, and you can also validate the time at which this occurs. And so it's, technically speaking, unbreakable, right, other than through social engineering, because it's just too difficult to break this up. So a hash, as if those of you are, if you're not a cybersecurity fan, a hash is a binary string using a specific algorithm that generates some type of a digital representation. It's a one-way function from a larger set of data. Every time you take that larger set of data and you hash it, you'll get the same number. You can't work backwards, right? There's too much entropy in the original data to get it from the one-way function, unless you just, sent like a painting of Klein, what Klein blue, which is all just one color. My guess there, you could technically hash them and you could get it backwards. But the bottom line is you're going from many, many bytes to just a few bytes. There's a specific algorithm that is digitally secure, and you can validate that the person did actually hash this by knowing what their public key is, okay? And the original binary string cannot be recovered from the hash, as I talked about. The odds of guessing another string resulting in the same hash should be equivalent to random guessing across the domain of possibilities. And that's what's super cool here, is that it should be very difficult for somebody to be able to get the same hash out of other content. However, that is changing as we move into quantum computing and as we've seen the explosion of GPUs to basically allow NVIDIA and others to make a lot of money off of people running a bunch of blockchain algorithms to get the next block in the chain. So for example, if you had 256 elements in a block, only 1 in 1.1 times 10 to the 77th strings will have the same hash as the actual data string, if your hash is actually only a 256-bit one-way function. Okay, so before an update can be made to the next and the next block added, the party must agree on a pre-agreed mathematical algorithm, and the other parties maintain a copy of the ledger and validate the result. So it has the same implications as a PKI, except that instead of going back to the CA each time, the CA managing the private and public keys, you distribute those once, and each person then posts their private key, their public key, and you can validate that they did sign that with the private key. And so that allows you to basically take the role of a CA and put it in the role of the consensus group that's there. So blockchains have varying size that can be used depending on the application, as we talked about before. And the choice of using only one may be an overfit. There may be times where you want a different blockchain for different workflows within a larger set of applications. That's okay. But this is a key trade-off point for the adoption of blockchains. Between immutability, we can't change them, and flexibility, we can add a new blockchain onto it. It's very difficult to override the functionality of a predefined blockchain, so you may wish to add another one onto that. And you can, of course, reduce flexibility by committing a majority of the peer cohort, that's the set of people who are involved in the chain, to a long future of workflow collaboration. And so again, the blockchain may be more difficult to extricate than other approaches from your business processes, another reason you may not wish to use those. All right, so there's a number of blockchain architecture options. I'm going to focus on the 3 primary ones: permissionless public, permissionless private, and then a permissioned private, I should say permissionless public and then permissioned public and private. Those are the ones we've got here. And a permissionless public blockchain allows anyone to be a user and remain anonymous. So you could see how that could be used for illicit purposes. You could have a permissioned public blockchain that has a particular company or stakeholder usually involved, or stakeholder set, who only allows known entities to be signed up. So as an example, you've got a supply chain application. The customer sets up their supply chain with all of their providers, all of their warehousers, all of their distributors, and then all of their end users. And each time a new supplier or customer is on board, they can be added to the blockchain. And then you have a permissioned private blockchain operated by only one user or entity. So this gives you an idea of the variety of distributed ledgers that are out there. We'll see blockchain appear in these, but again, look at the large number that we've got there. Here's where you see the permissionless and permissioned public blockchains. And we also see there's a large number of other ones, and I'll talk about a couple of these here, but this is mainly as a reference for you to see blockchain is not the only solution that we have for distributed ledgers. We have a lot of other ones, and that's pretty important. So increasing the size of a block in a blockchain is an exponential function in terms of cost and computing power as the degree of ledger distribution goes up. And at some point here, the distribution cost is exorbitant. The cost of being able to guess the next block with the hash algorithm that you've got, you run, as I said, trillions and trillions of hashes to get the next one that actually serves. That's a lot of energy involved. And of course, NVIDIA and other GPU makers have benefited from this as they've driven the costs of doing the blockchain algorithm way down by several orders of magnitude. In fact, it was in IEEE Spectrum a few years back, talking about how those have driven improvement in GPUs. And most of those have resulted in us being able to strip somewhere between, this is my speculation, somewhere between 12 and 20 bits off of most algorithms. And so that's moving those algorithms closer to their end game anyway. If you've got like SHA-2, it now has 12 or 20 less bits of protection than it had when it first came out because of this massively increased ability of GPUs to try to guess what the algorithms are doing. So it cuts across the whole security business, right? And so anyway, these conflicting components of blockchain adoption may be addressed by planning to use multiple blockchains so that you reduce the risk both in terms of the cost and in the terms of what's lost when this chain is broken. All right, so why do we use a distributed ledger technology? That's a DLT here up at the top. It has built-in security and trust. The added trust can create a lower transaction cost. And so blockchain algorithms can protect in time, temporally. That is, they can protect workflows and chains of events. And this is something that I spent a lot of time on with Helen Belinsky and others at HP Labs trying to figure out how we could actually set up workflows to be secure when they were conditional, when we could have possible workflow splittings and mergings down the road, and we didn't know what those would be a priori. So these solve a lot of that problems. It makes them readily amenable to supply chains and multi-party document workflows, and it's incorporated into multi-pathway security. Pretty cool. All right, so other secure DLTs, distributed ledger technologies. This is an example of a one-time pad. That's obviously very strong. The problem there is distribution. So you might be going, why aren't we just using one-time pads for everything? Well, we can only do those where we trust the distribution network, and we can only trust the distribution network when we have abilities to override it. So we did some work on this with, Chris might actually have been involved in some of this work, Chris Gunning, when we were working with ways to actually put secure distributed ledgers onto the printer. So a printer is a fixed asset, and the time when you update the one-time pad is when you have a service person come in and service the copier or the printer. So there are some ways that this makes a lot of sense, and I think we'll see one-time pads come back in transportation, as I'll talk about later. All right, let's see about this. I'm wondering why I can't hide this. Do you know why I cannot hide there we go, video panel? No, it won't hide it. Hide names. It's loading meeting controls. There we go. All right. I'm now able to do that. All right. Everybody's still following me, right? I haven't turned off the sound. All right. The one I'm talking about here is resource fairness. Many companies may be jumping on the blockchain bandwagon here without fully understanding some of the risks. So the first one, which is a pitfall of blockchain, is resource fairness. And we really need to be aware of that because it encourages massive centralization of computing power, especially GPUs, not as much CPUs because of the way the algorithm works. And it encourages specifically computing power for performing all of those hashes that are needed to find the next legitimate block. We also have some other controversies in terms of speculative mining. And this is particularly important as we start to see massively parallel GPU systems and the potentials, still unproven, of some of the quantum computing approaches. And so that if there's growing disparity in the processing capability of blockchain miners, then there's an increasing number of ways that a nefarious miner can pre-flight a lot of the blockchain speculatively, right? So minimally, they'd be able to create hash collision pairings. Now, you may have been thinking about that when I talked briefly about hashing before. You can have a large set of data, and there's enough play in here that another large set of data will end up with the same hash. Why is that? Because hashing is a converging application, right? It's a one-time function. But for example, suppose that we've got 64 different possibilities and we map them down to 2. Well, then we know 32 of these, all other things being equal, will map to the same one and the other 32 to the other one. So there is something called hash collision that can go on. And so pre-mining can look for ways to guess what the next blockchain is, and then it'll drive the cost up and wait until they predictably understand anybody else is going to be able to get the next blockchain and have the one after that already predicted. And so these are going to be based on predicting what the next version of the document may be and other speculations that are out there. So the would-be miner can automatically investigate a large set of potential substitutes for legitimate content to find an advantageous one that suits its needs. So imagine if you had a banking application and the loan amount was $1,000. And this miner goes through this and says, if I change the 1,000, turns out to $69,784.22, and then add these couple of weird characters at the end of it, it will then be approved for 69. So they go into the metadata of the file, or they go into a comment on the file, tweak it enough until they get it to hash the same with a much different value for what really matters, the payload of the cost. And for this reason, it may make more sense in a high expense financial domain like that to use something other than a blockchain if somebody can pre-flight this. Now, we haven't seen this happen yet, because obviously if anybody's able to do this, they're not going to report that. But it is a potential compromise. An agent with a disproportionate amount of processing power could go through and speculatively pre-compute what some of these are. Kind of scary. Let's look at active interference in a chain. So some parties may simply withhold separate legitimate threads until the value of the bit is right, and actively insert code such as malware or even instigate other cybersecurity attacks. So they could actually substitute in an extra set of data that's malware along with maybe some comments that are stationed in that, so that that gets read the same. And when somebody's reading this along the lines of how people are using, for example, bioinformatics. They're using genetic and metabolomic markers and systems that read those to inject malware as well. So there's potentially many correct hashes, as we just talked about. Especially the shorter the hash is, the much larger set of possible original documents that can be hashed to this. So a rogue participant with infinite computing abilities could engineer a blockchain for a wide range of nefarious tasks. Even if they don't do any of this, they'll try to withhold the single correct answer until it's most profitable for them and they don't feel anybody else has come up with the next set in before to increase the profitability of mining. There is absolutely no reason they wouldn't be motivated to do that, to withhold the next one in a blockchain until it's the maximum profitability. And that's why we see so much volatility in blockchain algorithms. All right, another thing you could do is also use your computing power for denial of service attacks and introduce volatility into the chain. So a supercomputer speculates several steps ahead and finally guesses one such double step. This computer can then go to other mining computers into searching for the next step while it's looking two ahead, and it releases the next step they've been looking for before they can find it, and then it has the next step already ready to go, and it can predict when to release that based on what's going on. So firms will become aware of alternative ledger technologies that could help them achieve the desired things without putting themselves at risk that's there in some blockchain implementations. And again, why would the additional cost and complexity of doing a blockchain algorithm be employed where a simple PKI can suffice? Well, we saw some of the reasons for that early on. We might want to have a given set of participants, and we don't want to have to go back to a CA or a certification authority multiple times. So there are some advantages. We trade those off, right? Another one is sustainability. I think we've made this one pretty clear. That's a concern precisely because the blockchain algorithm has inefficiencies in processing time. And right now, blockchain and Bitcoin are estimated to have the current carbon emissions footprint as a country as Sri Lanka, and double that if all the cryptocurrencies were included. So that's a lot of carbon being spit out just to do an algorithm. And to me, that makes it be an example of something we probably shouldn't do given where we are in the world, right? As blockchain is used today, is incapable of supporting even a modest fraction of the world's commerce, but it's already burning as much energy as a medium-sized country. So that's kind of scary, right? So there's good examples. There's mining operations in Inner Mongolia and China containing tens of thousands of Bitcoin mining machines, and they're all generated by coal, right? So let's take a look at the scale. I alluded to that on the last transaction. It's a little back of the napkin measurement here. Visa processed 111.2 billion transactions in the last year I was able to capture, 2017. Right? So it's estimated that a single Bitcoin transaction uses 5,000 times more energy than a single credit card transaction. So we can assume the mean transaction size is roughly 250 bytes, and a block in the chain is limited to 1 megabyte, indicating a block can contain about 4,000 transactions. So we get to divide that by 4,000 before we start looking at the cost of the blockchain. A block can be published to the blockchain only about every 10 minutes for the purpose of ensuring that not too many Bitcoin blocks are produced. So 4,000 transactions are processed every 20 minutes, about 6.6 transactions per second. Visa alone processes 3,524 transactions per second, 3 orders of magnitude more than blockchain could handle. So we would actually not be able to do all of those. We would require management of multiple blockchains, which gets away from the point of having a single ledger. So scale is definitely a concern there for some of the larger scale transaction spaces. Track and trace, there's a cost associated with collecting information from multiple parties related to the shipment. So many supply chain companies see potential to provide a visible history, but we already have provenance approaches, as I alluded to before, which is sender receiver signing when they send and when they ship and when they receive content. So material provenance in helping track and trace, like raw materials to avoid conflict minerals or produce grown here is another example, or other distributed ledgers can contain some of the same features, right? So really what we want to do here is use it for visibility. And then of course the financial cost, all of the algorithmic calculations that we have to do these speculative hashings until we get one that gives us the required number of zeros at the front of the hash are done by computers in a process called mining, and it takes substantial, we're talking, gigawatts of energy to compute that, because they're going through so many trillions of computations by the time the blockchain gets to be any length at all. So the IT department may be undersourced to be able to keep up with this, aren't going to be able to compete in processing with somebody else. Why would you put yourself at risk? So there are some concerns there with that. Okay, I think that gives you a good overview of blockchain and gives you kind of an idea of what we're looking at. The specific paper that I was invited to talk about, I'm only going to spend a few minutes on because it's my paper and because I'd rather talk about things that are of more global and general interest. However, there are some neat aspects to this paper that I think are worth sharing. So this is the name of the paper. It's Blockchain Technology in the Smart City, a bibliometric review. And so there's some terminology there that I want to make sure makes sense. Biblio obviously means book or library, and then metric is measuring that. So this is basically a large database of other content, reviewing that and putting that down to kind of give you the gist of what's going on. So this is not a traditional research paper, it's a bibliometric review paper. All right, so blockchain, and that's where it is online if you want to go see it. Blockchain can function as a foundational technology with a lot of applications in the smart city, right? So what we were doing in this is we're doing a bibliometric review using keyword co-occurrence networks and article co-citation analysis. And all you're doing there is saying, are there themes, whether they're keywords, or are there themes, whether they are sources of other information that are correlated between multiple sources of information, papers, journal articles, et cetera. And this is not that different from PageRank, which of course was the underpinning to the original Google engine, right? PageRank is like saying, oh, something is a more valuable source of information if it has both a lot of links to it, and then the things that are linking to it, usually the resources that are linking to it would be other URLs, if what's linking to it also have a lot of folks linking into them. So it's like you've got powerful links that are also highly linked, et cetera. And so that's kind of what we're looking at here, something analogous to that. So the bibliometric review uses this keyword co-occurrence. We found about 150 articles that applied in 76 academic journals, and the number of articles devoted to blockchain applications in smart cities has clearly, as you'll see shortly, increased exponentially. And then we're also identifying some of the most influential studies and trends in this. So smart cities are the next generation of urbanization. Here's a, I wish you went to a city once that was this clean. I guess Singapore is kind of like that, right? So sustainability and efficient urban center, high quality of life, advanced physical infrastructure, availability, integrity, and quality of knowledge, communication, and social infrastructure. Those are the 5 key aspects of what a smart city is. If you hear that term, sure you do, it's kind of a buzzword at this point, right? So they have advanced technologies and intelligent networks, which are enablers, broad infrastructure, government e-services, wireless communication networks, high-speed security protocols. So these are some of the questions that we're looking to solve in the paper. How did blockchain and smart city research evolve since it started? What are the leading countries and journals publishing? What are the critical research hotspots? Where is this going to go? Where's blockchain going to be used in smart cities? And which articles are most influential? Now, here's some details about it. I won't elaborate on these points, as our little plankton asked to elaborate earlier. This is the Scopus database, et cetera. And we basically did a search operator with blockchain and smart cit, which is basically saying this is our, lemmatized version of cities, et cetera. Okay, in English before 2021. So we ended up with bibliometric methods, you end up with a descriptive analysis of selective publications. And this is an example of what we get when we've got FOSS Viewer here with all of the attributes there, kind of a word cloud, if you will, in a kind of a linked form. And so that was our visualization software, VOS Viewer. Keyword co-occurrence analysis allows us more in-depth understanding of what's going on there, cite and co-citation analysis, as I alluded to before. Let's get to some of the numbers from that. This is where blockchain and smart cities are going. So if you pair 2 buzzwords like blockchain and smart cities together, you would expect to see some exponential growth, right? Because it's basically doubly, what would you say, buzzword bingo type of situation. So we obviously anticipate the number of publications incorporating blockchain and smart cities to continue a clearly exponential increase that we've seen already. Not surprisingly, the big computer science countries, China, India, and the US, South Korea, UK, Australia. I'm not trying to leave everyone out, but in the interest of time, you can see the rest of them here. That's kind of where you see a lot of the forefront of computer science going on. No surprise it's correlated here. And with the blockchain implementation, US state and authorities and local governments aspire to improve those types of things. That's what we've driven out of there. Here's the journal distribution. You can see there's a very prominent others here, which means these are distributed pretty well. There's a diaspora of this technology from places like IEEE, Internet of Things Journal, and IEEE Access. It's really nice to have Chris here. I didn't plan on that, but there you go. The top 2 journals for this topic are IEEE journals. Some of the other ones are obviously ACM journals. Sensors is a well-regarded journal. Sustainability is as well. And so again, these are much less so for management, business, urban sciences, and social sciences journals. Those will typically matriculate after it's gone through the engineering round. You'll see that leveling off and going into other journals. All of these, for the most part, are in engineering journals. This is probably of interest. No surprise here that blockchain and smart city are the top 2 elements in the co-occurrence. It'd be kind of surprising if it isn't, because that was our search term. So that'd be really weird. But again, look at what's number 3. So you start to look at these and go, these are the ones that are actually going to be moving from the periphery, right? So you think about punctuated equilibrium in evolution, right? Punctuated equilibrium basically means that things evolve really, really slowly, and then all of a sudden, bam, they get punctuated and things change very quickly. Stephen Jay Gould and others have championed that, and there's a lot of historical record to support that. There's also a lot of social science network to support that. We can kind of see where things are going, and they come from the periphery. Is it going to be IoT? Is it going to be security? Is it going to be privacy or smart contracts that really drive how the smart city and blockchain work? I expect it to be all of them, but these are the ones that you see growing in size. And what we did out of this is we found clusters that had, more correlation internally than they had with the other groups. Those are kind of the clusters that you see around here, one around the core, this one here around kind of smart grids and machine learning, kind of advanced algorithms, and we'll talk about each of these briefly. But sustainability represents the furthest research topic from the mainstream right now. Sustainability is over here, that's the core of this block. Will that actually be something that then moves this out, allows us to expand more? All right, so these are the 10 most frequent keywords in each cluster. If you're looking at clusters 1, 2, 3, 4, 5, and 6, we gave them the title for their primary one, blockchain. Not surprising, right? That should be in there because we did the search on blockchain and smart city. But you'll notice smart city is the second key term under there. So blockchain is actually leading this combination and not smart cities. That kind of makes sense. A blockchain is something you use to help create a smart city. You don't use a smart city to help create a blockchain, in case you're wondering how that works. And then we've got machine learning. That's what ML is, security, smart contracts, smart community, sustainability. And I think, you look at each of those, and again, these are the top set of keywords. After that, in some cases, the keywords dropped off too quickly for us to count any of them in there. Kind of nice. I don't know what you take from this, other than the fact that, wow, there's, we would expect to see security in there, but machine learning kind of is interesting because blockchain is not really a machine learning process. It's a known algorithm, as with most security. You publish the algorithms that you have there, and that fits into Kirchhoff's principle. These are the most cited articles. I leave these as a reference for you. I don't know if there's any real take-homes out of that, but you do see there's a lot of differential choices from these. These are the number of citations they've had. This article has already been cited 548 times. In case you're wondering, that's a lot to have an article cited. All right, so some of the knowledge gaps, I think this is important. These are where we're actually looking to go deeper in the future. So blockchain and other distributed ledger technologies for economic, social, and environmental dimensions of sustainability. No idea where that's going yet. And then blockchain, IoT, and big data, how they combine to create smart cities. The IoT is a huge thing. We aren't currently using blockchain for a lot of the distributed sensors that are in there. Is that going to be actually what drives it down the scale? And you can read the rest of these in your leisure time if you have any. Who has leisure time anymore, right? All right, so our next section is verticals of interest. And I'm, again, going to gloss over these. You could do an independent talk on each of these, but I want to show you how we've taken what we had in the paper and what we know about blockchain, combine those into saying, where are we going to go? So traditional manufacturing, trust is tied to centralized security processes. So you've got your public key infrastructure, your PKI, you've got LDAP, you've got access control lists. There's a number of ways of managing the access that we give to people. But with custom manufacturing, where we have all of these extra, and we'll see these in the next few slides, where you have all of these extra ingredients brought into manufacturing, the trust is tied to the elements that are working together to produce custom parts. And blockchain is a minimal chain of elements to produce the custom parts. So let's take a look at what this actually means. Custom manufacturing is a manufacturing process where the components are specified at any level below 100% of the part. So we have custom manufacturing as opposed to typical mass production, where these are running through and each box is basically the same. So an iPhone case with special text on it, right? If you have an iPhone case that has a message on it that's personal to you, that is actually custom manufacturing. As it turns out, more important than custom manufacturing for the world we live in, which we ultimately have to take into account, is decustomization, which is a name that I gave to taking mass customization and fitting it into mass production. So we got a mass production system. You go to them and you say, you need additive manufacturing and all these, and they'll say, here's my books. I owe payments on this mass production system of mine for the next 10 years. So you're asking me to get fired and the 10 people who come after me to get fired before we actually start making money off of this. Instead, what you do is use things like additive manufacturing or 3D printing, that's what 3DP means, to fit these parts into an existing production line. And that's kind of what we're doing with blockchain. We may have it fit into a mass-produced security system and use it only for the custom elements that we need blockchain for. Okay, this is just more fun with manufacturing. These are examples of why manufacturing is more complex. If we go from just having a mass production brand to having open source things like Thingiverse and MakerBot, or local expertise, a mom and pop shop who are running a maker store, you've got 7 ways to manufacture: A, B, or C, A, B, A, C, B, C, or A, B, and C combined. And there's all these failure modes, which makes it really open to perhaps using blockchain processes, distributed ledger processes, for indicating how to test when a failure occurs, whether it's any of these. And of course, this will have a lot to do with who is responsible for the failure that's out there. And I'm not going to go into a lot of details here. I'd love to, but it's a fun topic, but this is a 10-minute slide. And this gives you more on, again, IEEE. It's almost like Chris helped me make these slides. I love it. So this is IEEE forensics and failure analysis that's going on. These are the different ways that you can be accountable or liable for this. Pretty cool stuff, but I'll talk more about that probably in the talk I'm giving on April 13th at Boise State. What about energy? What about the energy environment? Another big vertical, right? How big is energy? It's huge. It's trillions and trillions of dollars a year. So cyber physical security approaches have to involve sensor authentication, right? If we're actually moving this out to distributed energy and you've got solar panels at home or you've got a little windmill at home, how do we know you're not spoofing the system? The threat surface goes way up when you go to that. So we need to have sensors digitally signing. That sort of fits into having the, well, you might have a trusted platform module or something else that assures that on there, but you've got a private key that's on each of those sensors that we want to have be able to, or we might have a nonce, we might have a stored secret, or adaptations of these for sensor population. So yes, there's a lot there as energy also moves out to being more distributed. What about transportation? Well, we're seeing the possibility of a lot of autonomous vehicles coming out there, right? And we also have drones and other things that are working together. Well, what's happened to us is the same thing that's happened to us in other areas. This phone that I've got now, not particularly new, a year or two old iPhone, has far more computing power than the Cray supercomputer I used to do my imaging when I did the first reconstruction algorithm for impedance tomography way back in the late 80s. I mean, that's a supercomputer. Every car now is a supercomputer. And part of the servicing will be supplying a new set of nonces. A car maybe, and you will see this, as you have autonomous vehicles out there, there'll be a certain percentage of autonomous vehicles that are just out there to swap out real-time batteries on autonomous vehicles so they don't have to go with the downtime of a recharge as we start to build those out. So you'll have a supported vehicles that will be on-the-fly battery refreshment, as I talked about here, and you'll also have ones that are digital resupply. If you're delivering a new battery, provide new digital resupply so that these cars can't be hacked. I'm sure you all know that vehicles that are out there are very easy to hack. We do a lot of work on that in our cybersecurity program here at CSU, right? All right, so clearly that's going to be more. What about precision agriculture? Absolutely the same, right? The farm simply has to be more sophisticated. Monocultural movement will be replaced by hybrid models where we're growing multiple crops in the same field. And we use computer vision and other advanced artificial intelligence, AI, to simultaneously harvest multiple crops and eliminate the weeds. And each element is a node for consensus. So I actually have a patent in this space. This sounds really kind of elaborate. Really what this is a 3D printed potato with an energy scavenging sensor set inside of it. That's what I built. I used my 3D printer because the potato is not hard to make. With 3D printing, it doesn't need to be precise. It's kind of, and so what I did was I had a energy scavenging system inside of there so that when this fake potato was going through the harvesting equipment, rather than it being chopped up into a bunch of electronics that probably would make a even worse French fry than some of the fast food ones. It was set up there so that it would gain enough energy rolling through this to send out a radio signal that says, please collect me and don't try to turn me into French fries, right? Kind of cool thing, kind of a little one-off type of thing. Operations are another area that we're going to see with blockchain being applied. Mass serialization, which means every item that's produced has its own unique number. Now, as you move into custom manufacturing, you're going to need unique numbers for all parts of that. That's super cool. And so mass serialization and the sequential signing of content by each sender receiver, which GS1's been doing for 40 years, right, is going to continue to be part of this. But we are going to use blockchain in some elements of it. And then, of course, operations, right? So currency is one of the most commonly counterfeited products on the planet, right? Even coins can be counterfeited, right? Because you can actually have a gold coin like a Krugerrand or something like that. I don't even know what those are worth now, maybe $1,000 for a little coin. And you can actually simulate the gold by having a really thin gold coating. And if you wonder how thin gold can be, you can actually cover a tennis court with gold for an ounce of gold. It can go that thin. I think the actual layer of gold that's on top of something that's been gilded is only two molecules thick, right? And so you can do this for less than 20% the cost. If you want, I can actually show you how to do this on the benchtop using iridium and lead to get the density of gold and then just gold coat it, right? So one of the things I got to do at HP, I was involved in security, but also security printing, much more so for the last 15 years I was there. I got to do a lot of ethical hacking of cyber physical security, so a lot of counterfeiting of products, right? All right, let's take a look at some other perspectives, right? We've got Ego there from Ratatouille, an S-tier movie if you haven't seen it. What's wrong with you, right? All right, so anyway, this is a parody of his quote, and these are now the perspectives. So you're like going, wow, I listened to this whole talk. Is he going to drive any points home? Well, this is the time I drive the points home. Illicit trade thrives on opacity or the lack of transparency. So if we are harkening back to the original slide where I talked about don't use blockchain for this. If you've got a blockchain that is there intentionally creating opacity, removing transparency, it's most likely being used for something illegal. And we see this all the time on the dark web and not the non-dark web, the regular web, right? People are using blockchains to hide who the people involved are. If you don't know who all the people are in that ledger, you should be suspicious. Illicit trade thrives on volatility, as we said before, and this is one of the things that adopting the blockchain algorithm for all of the distributed ledgers is not necessarily a good thing. And illicit trade, if you think, oh, who cares, right? And we used to get that when I would talk to people about how HP had billions of dollars of counterfeiting, people would go, oh, wah, I really care about HP. They've got deep pockets. Yeah, well, the problem is that illicit trade can take down nations. And I worked on the model for this for 6 years when I was part of the World Economic Forum's Global Agenda Councils from 2010 to 2016. And great gig if you want it, but I got to meet Peter Gabriel, for example. It's a great gig. Anyway, illicit trade can take down nations. We put together a rule that said 30% gray market will actually remove all of the taxes that do all the value in the country. And they do. About 50% of your taxes go to keep the government open. I mean, government has buildings, they have lights, they have toilet paper, they have, people with benefits and all that. We want that. The next 50% of your taxes pays for all of the things the government does. And if you only do 40% of that 50%, so you have 30% removed, this is 60% of the actual payload that's there, the government just does cronyism and favoritism and nepotism. They support their friends of the government, and everybody else in society loses their benefits. And so 30%, basically the country is no longer a country. And we saw that with looking at the numbers we got from Bosnia-Herzegovina in the 90s, Somalia in the 2000s. We applied it to Venezuela and said Venezuela will go down in 4 years, and it did. Right? So this is a big deal. And blockchain is driving a lot of illicit trade. It's driving a lot of human trafficking. It's disgusting. And so make sure that you're not involved in some type of a blockchain like that is actually leading to these things, right? Can drive child trafficking, general human trafficking. I'm actually doing a presentation which will have some of these ideas in it next week at CSU's Human Trafficking Symposium, run by my good friend Lumina. All right, so complacency and security is the best ally to illicit economies. Don't be complacent. Think about why you're using this. Here's a happier perspective, the perspective of the public key infrastructure. So other forms of PKI, for example, fiducials, can be highly valuable. We can do that for cyber physical security. We built little imaging devices that do that when I was at HP. GS1 model in history, sender receiver signing. All right, so you got a CA involved, but the CA distributes the same set of private keys and public keys, and you just use those to sign and receive thereafter. It is technically just as secure as the blockchain itself. Cyber physical security is best implemented with dual or more factor authentication approaches. So why not use dual factor authentication instead? Think about where you can use that. And by the way, if you're signing on without dual factor authentication, in this day and age, it's kind of a threat surface. It's a high vulnerability surface. Okay, a public key can be shared with all, right? That's a nice thing. And Kirchhoff's principle still applies. I think I spelled that right. That's a tough name to spell. The security of a crypto system must provide no larger threat surface than the choice of key. And everything else is public knowledge, and without the key, you can't do anything with it. We know that's the case for a one-time pad. Unless you know the exact XOR that's been used, every single possible interpretation of those bits is equally likely. So we aim to do that with anything else we're deploying. So keep that in mind. What about the perspective of perspective? I don't even know what that means. Context is important, right? So you need to assess the context in which you wish to employ your DLT. From those options, remember that table I gave a few times back, there were like 8 or 9 different options for digital ledger, distributed ledger technologies. And number 2, smart is not about selecting the most complicated solution. Just because you can do a blockchain doesn't mean you should. There is complexity that's involved, and there's also, the sustainability aspects and others that we talked about. The other thing to remember is blockchain is a tool. It's not a system. It's a tool that's used, just like PKI. So don't get enamored with it as if it's something else. It's a tool, right? It's no different than a hammer. The most cyber secure system is one with no access. So reducing the threat surface is usually a better investment than employing the latest DLT approach. Look at what your threat surface is and try to reduce that first. Number 5 here, perspective of perspective. Until tools have been used in at least a multiplicity of application spaces, they're unproven. And our analysis from the paper is that only transportation, healthcare, and operations have begun deploying blockchain in force. We still haven't heard back the word on those where they're going to go, but those are going to be very important. So again, these are some of your, well, here you go. There's 7 right here. There's 7 different distributed ledgers I've identified as being ones to choose from.